Okay, we're going to do a little bonus feature with the Rayleigh probability distribution stuff. Bonus problem. We're going to use a dartboard again, and we'll say, here's our little contest. Two players get one dart. Whichever player's dart is closest to the center wins. And we're going to assume our players have Rayleigh probability distributions in their miss distances. Talked all about these probability distributions already. And we'll assume their throws are independent of each other. What's the probability that player one wins instead of player two? And these, for example, could be different PDFs associated with different players. Maybe player one is green and player two is red here, all described by their little sigma values. So a smaller sigma value means closer to the center. So you'd think the guy with the smaller sigma would win. What's the probability of that? In general, how do you go about such problems? We're looking for a probability. If you have a PDF probability density function, if you integrate the PDF over a region of integration, that's the probability of your random variables being in that region of integration. If you have just a single variable, it's this thing. The probability that X is in this interval between A and B is just this integral of the PDF from A to B. If you've got two random variables, bivariate PDF, you have a double integral over the region of integration, which is in the XY plane. The region is in the XY plane, the plane of your random variables. So what is it here? Well, let's see. First, what is this PDF in our case? Well, here's the Rayleigh PDF for player one. Here's the PDF for player two. Since they're independent, the joint PDF is just their product. So this is the joint PDF. So we have this guy. Now, what is the region of integration? Player one wins means his miss distance is smaller than player two's miss distance. Well, our two variables are R1 and R2, the two miss distances. Region of integration is in the R1, R2 plane. And those Rayleigh distributions are only non-zero for R's greater than zero. So we're definitely going to be in the first quadrant, right? But also, where is this true? R1 equals R2 at this straight line. R1 equals R2. And up here in this shaded region is where R1 is less than R2. So we had our PDF. It's all this guy. Our region of integration is where R1 is less than R2. And that means this. Integrate R1 from 0 out to R2. Then integrate R2 0 to infinity. Our remaining job is to evaluate this integral. And I'll try not to get too painful with that. So here's where we left off. First, if you look at this inner integral, anything that doesn't involve R sub 1, we can bring out of the inner integral. So that's this over here, which leaves this as the inner integral. Well, this is just integrating the PDF of a Rayleigh distribution out to some number R sub 2. And when you do that, you're actually taking CDF evaluated at R2. This. So this is what's up in these parentheses. So now we're to this. And we can break that up because you got a 1 times this minus all this times this. So here's where we left off. This part, again, well, this is the PDF evaluated over all R. That's 1. So this whole front part is just 1. This guy, we can change it a little bit. I wrote it. Then I'm going to substitute a number here. I'm going to say define this plain old sigma without a subscript as being this part up here, that there, which means it equals this. Anyway, I don't want to go through this too much. So we have a 1 over sigma 2 squared here. That really is all this. So we can pull out this part up here. Here we have an R2 over just the sigma part. Here we replaced this mess with just this guy. And again, this is PDF integrated over all R. That's 1 again. So there's our answer. And actually, that can be written this way. Here is our answer. The probability that player one's dart hits closer to the center of the dartboard than R2's dart is this guy. And by the way, since CEP is just a scalar multiple of sigma, this is the same relationship. We have CEP instead of C. Anyway, that's all with that little problem. That really should end what I have to say about it. By the way, I had to do that problem for work. I got paid to solve that problem.